In this lesson, we're going to cover the integral test and a direct consequence of it, the p-series. So let's start with the statement of the integral test. So here we have it. The integral test says the following. Suppose that f is three things: continuous, positive, and decreasing on an interval c to infinity, where c is just some real number. And let a sub n, which is the series nth term, be f sub n, f of n for this function f. Then our series which goes from c to infinity, and incidentally c is 1, is typically the most common way of applying this, and in fact some books state, in fact this book did, and I changed it to c. It doesn't matter, doesn't absolutely have to be 1, it has to be just some real number, but 1 is the most common. Then the series from n is c to infinity of a sub n is convergent if and only if the improper integral from c to infinity of the function is convergent. In other words, they behave the same way. If the improper integral is convergent, then the series is convergent, and vice versa. If the improper integral is divergent, then the series is divergent. So let's just have a quick peek at a sketch of a proof here as to why this works. So this is not an official formal proof, but just an idea of why this is reasonable. So if we look first in the convergent case, and here is the graph of our function. Here's the graph of our function f, well, it's f of x, and the area here, which is in green, if this is convergent, then that area is finite, right? That's finite area. So what we're going to do here is build a graphical representation of our series, because the series term can be obtained from the function, right? So a1, right, is obtained by plugging 1 into the function, and a2 is found by plugging 2 into the function, and so on and so forth. So we have this bunch of points. I was going to say series of points, but we don't want to use the word series. We have this bunch of points here on the graph where the y-coordinate is the series term. And, well, we can sort of do like we did with Riemann sums. We can make rectangles with these, and if we make our rectangles here using right endpoints, then the y value, which is the series term, is the height of our rectangle. And if I choose to make them spaced here with a delta x equals 1, then our base is 1, and the rectangle here, the area of that rectangle is base times height, so is 1 times a1, so that rectangle has area that is equal to the first term of the series. And I do that for each term using the right endpoints, right? a2 is the right endpoint here. If I make a rectangle, its height is a2, its base is 1, so its area is a2, and so on and so forth. So what we have here, right, the sum from n equals 1 to infinity of the series can be rewritten. If I take a1 out, then I've got the sum from a2 to infinity. And why would I do that? Well, a2 and a3 and a4 and all of those rectangles are underneath the function graph. And if they are underneath, then clearly they represent an underestimate. So this, oh, there's a term missing here. This one here, that is less than the area of the function. And if the area of the function is finite, then the series must be finite because it is less than it, right? So that is an idea of why this works in the convergent case. So let's go and look in the divergent case. Well, what happens there? If this integral diverges, well, that means that the area under this function graph is infinite, right? How do we know it's infinite? It can diverge for all sorts of reasons. Well, if this is a positive decreasing and continuous function, then it must be infinite area, right? We have no area underneath canceling out. There's no oscillation or anything of that nature, so that area is infinite. And now what we're going to do is we're going to build rectangles, but using left endpoints. So here is the same point 1 and A1, but if I build a rectangle using the left endpoint here, then I'm clearly getting an overestimate. There is more area in those rectangles than in the under the function graph. And so the series, if I add up all of those rectangles, then the area there has to be more than the area under the function graph. And if the area is infinite and this is bigger, well, then it's infinite too. It's infinite too. And so that sort of shows you why these things behave the same way. If the integral converges, the series converges, and if the integral diverges, the series diverges because of how you can play with rectangles using either left endpoints or right endpoints. All right, so that's just an idea of the proof of why this is reasonable. So let's go and actually apply this test in a couple of examples. And to apply this test, and really to apply any theorem for that matter, it is essential to check that it applies, right? That its hypotheses or its conditions are met. And in the integral test, we had three. We had that the function must be continuous, it must be positive, and it must be decreasing on the interval that you're looking at. And so in any time, in any problem where you apply the integral test, it is mandatory, non-optional, mandatory to check that these three conditions are satisfied. So let's go ahead and do the following exercises. We're going to apply the integral test to determine convergence or divergence of the following series. And that means we're going to check the conditions. So let's look at this guy. So the integral, or the series, the sum from n equals 1 to infinity of 1 over n squared plus 1. And incidentally, the integral test would not be my first choice. It's the first choice of test that we have seen so far, but we are going to see another test soon, which would be quicker and easier. But the integral test is not wrong. The integral test is a little bit like a sledgehammer, right? It's very heavy-handed, but it gets the job done. But it is a lot of work typically, and it is often your test of last resort. It's the test that you apply if nothing else seems to cease to do the job, nothing quicker and lighter. So this example, we're going to do the integral test to show you how it works, but it is actually not the test that I would choose for this series in an ordinary situation. So let's go ahead anyway and apply the integral test, because that is what the question asked us to do. So the first thing we identify is that our function, if our series term is 1 over n squared plus 1, then we have a function that matches. F of x is 1 over x squared plus 1. To check that the integral test applies, we must see that the function is positive, continuous, and decreasing. Well, positive is pretty easy. Positive is pretty easy to see, right? X squared is always greater than 0, so x squared plus 1 is greater than or equal to 1, and so 1 over it is positive. It's positive on R, so it certainly is positive on the interval that we're looking for, right, which is from 1 to infinity. Why 1 to infinity? Because that are the bounds of our series term. Continuous. Well, the domain of this function is the reals, right? And rational functions are continuous on their domain. So it is continuous on R, and therefore continuous on 1 to infinity. And decreasing. Well, we have a fantastic test for decreasing functions from calculus 1. A function is decreasing when its derivative is negative. So we go here and we calculate the derivative. If I rewrite f of x as x squared plus 1 to the minus 1 power, then f prime is applying the power rule and the chain rule. So I get minus 2x over x squared plus 1. And that is, well, the bottom is always positive. We just said that before. So this is negative when the numerator is negative. Minus 2 is already negative, so it is negative when x is positive. So on 0 to infinity, so clearly on 1 to infinity as well. So we have our three conditions. So we can apply the integral test. So the integral test tells us to compare the improper integral with the series. Well, not to compare them, to use the improper integral to predict the behavior of the series. So we're going to look at this improper integral, which means that we need the limit from as t goes to infinity of the integral from 1 to t of 1 over x squared plus 1. That antiderivative is arctan. So we're taking the limit as t goes to infinity of the arctan from 1 to t. So here is that limit, and the arctan function, we've used this several times already. The arctan function as you go to infinity goes to pi over 2. Arctan of 1 is pi over 4. This gives us a value of pi over 4, which is actually irrelevant as far as the value goes. It converges. That's the important part. So because the integral converges, this series behaves the same way. It converges also, but not to pi over 4, right? It does not converge to the integral value. In fact, we saw up there that it converges to something less. We don't know. We don't know the value of this integral using the integral test, right? This is a pass-fail test. This is pass-fail only, and we have passed, we have converged, but we do not know the value of that series. That is very important to keep in mind. The integral test is not giving you the value of the series. It is simply pass-fail. So, second example here, and this one I would choose the integral test to, or yeah, maybe not even. So, here is our next series, the series from n equals 1 to infinity. As I say, the integral test it's a heavy one, right? It's the one that you choose if nothing else works. And now that I look at this a little bit more carefully, I don't think I would even choose the integral test for this. But to exemplify why the integral test applies, or how the integral test applies, let's go ahead and apply this anyway. So then what do we have here? We have a function, right? We have a function f of x is ln x over x, and so our series term is the function applied at some integer n. We have to check that the function is positive, continuous, and decreasing. So positive, well, we're looking at the logarithm. The logarithm is positive on 1 to infinity, and so ln x over x is positive on 1 to infinity. It is continuous. The domain of this function is from 0 to infinity, and this function is continuous on its domain, so it is continuous on the interval that we want from 1 to infinity. It is decreasing. Again, we look at the derivative. The derivative is here, so we're using the quotient rule. The quotient rule, which ends up by giving me 1 minus ln x over x squared. This is a positive denominator, so the derivative is less than 0 when the numerator is less than 0, which, if you solve that inequality, so 1 is less than ln x is greater than 1, which is x is greater than e, so on e to infinity. So you'll notice that those do not match. Those do not match. That is okay, as long as these things are eventually, as long as they are eventually true, right, at some constant to infinity, then it is fine. And so you might say, well, shouldn't we be taking the integral here from e to infinity since everything sort of works from e later? Yes, but no, it really doesn't. It doesn't matter as long as we have continuity from that interval. We can use the continuous interval as long as this function is eventually decreasing. So this is kind of the more important of the bounds to apply. But certainly we could do it from e to infinity. We could do it from any point past here to infinity, and we would get the correct answer. Obviously, the value might change of the integral, but the behavior, convergence, divergence, would not. So let's do this integral, the integral from 1 to infinity of ln x over x dx, which is a limit. Limit as t goes to infinity of the integral from 1 to t of this ln x over x. Using a little substitution on the side, we're getting the antiderivative here. Antiderivative that we're looking for is 1/2 ln x squared from 1 to t. This has a, we're taking the limit of this, and this should now be a t value in here. This should be t. And that, the logarithm as we go to infinity, the logarithm goes to infinity, and if you square it, you're only getting to infinity faster, and so that limit is infinite. In other words, it does not exist. So the integral has diverged, and the series then also diverges, and that's it. That's it for the integral test. So I was looking here, right, at both of these I said were series that I would choose something other than the integral test. One that I might choose the integral test on more precisely. That's not what I mean. The integral test is the better test to use. For example, would be maybe one like that, where the integral test is the kind of the only choice that you have, but it works exactly the same way. So let's look here at a P series. So the P series test is a quick one. It's a direct consequence of two things, of the P integral that we looked at before and of the integral test. And so what it says is this: if we have a series of the form, the sum from n equals 1 to infinity of 1 over n to the p, well, it converges if p is greater than 1 and diverges if p is less than or equal to 1, exactly like the P integral did. And the integral test tells us the series behaves like the integral. So it is identical. It is identical in terms of behavior to the P integral. So quick couple of examples here with the P series. Let's look here. The sum from n equals 1 to infinity of 1 over n, which is 1 plus 1/2 plus 1/3 plus 1/4, going on forever. This is a famous series called the Harmonic Series. It is a P series. It's a P series which has P equal to 1. And since P equal to 1 is less than or equal to 1, right, that is the test here for divergence. In the divergence case, it diverges. However, n equals 1 to infinity of 1 over n squared converges. It's also a P series since P is equal to 2, which is greater than 1. Now, one thing I want us to point out, our last test was the nth term test. If we tried to apply that here, if we did the limit as n goes to infinity of a sub n of both 1 over n and 1 over n squared, we would get 0 for both. And yet they behave differently. One diverges, the other converges. And so that was something that I had pointed out to you in the nth term test. If you get 0 for the nth term limit, then you know nothing. Either behavior is still possible, right? The series might diverge like the harmonic series. It might converge like 1 over n squared, right? So that is just a little reminder that the nth term test limit, if it gives you 0, you are no further ahead. The nth term test tells you only divergence if that limit is non-zero. So two last little examples real quick. If we have the sum from n equals 1 to infinity of 1 over n to the e, this converges since e is the power, which is approximately 2.718, and that is greater than 1, and so we have a convergent series. Number 3, the sum of from n equals 1 to infinity of 1 over root n diverges, since root n is 1/2, so the p is 1/2, and that is less than or equal to 1. And it is really that quick and that simple for the p series.